Welcome students to our new YouTube channel Pharmatech, the division of excellence. So let's start to our new chapter, that means chapter number 9, buffers, and also says buffer solution or buffer system. So let's start to this chapter buffer. So in that we first study what is buffer, that means the definition of buffer. A buffer solution is one which maintains its pH fairly constant every upon the addition of small amount of acid or bases. That means a buffer solution resists a change in its pH. Then next we see the study two common types of buffer solution. There are two types such as acidic buffer or basic buffer. First, acidic buffer. Acidic buffer, it is a weak acid together with a salt of the same acid with a strong base. For example, CH3COOH plus CH3COONA. That means CH3COOH and CH3CONA are the buffers. That means acidic buffers. And the second one is basic buffer. Basic buffer, it is a weak base and its salt with a strong acid. For example, NH4OH plus NH4Cl. Then next we see the mechanism of buffer action. First, for acidic buffer, that means CH3COOH and plus CH3COONA. Such a solution will contain excess of acetate ion and a large amount of unionized acetic acid and a small amount of hydrogen ion formed by original conations of acetic acid. Then next we see the addition of HCl to this system or H plus. On addition of H plus to this system, the H plus combines with the acetate ions to form more unionized acetic acid. That means H plus CH3COO minus, it gives H2O plus CH3COOH. Thus the hydrogen ion is added or removed by excess of acetate ions already present and the solutions will retain its constant pH value. Then next we see the addition of base such as sodium hydroxide. When some base such as sodium hydroxide is added, the hydroxyl ions added will be removed by reaction with acetic acid. The OH minus plus CH3COOH minus, it gives H2O plus CH3COO minus. Thus again the solution will maintain a constant pH value. That means in both cases the addition of HCl or and H plus and also the basic medium such as sodium hydroxide, the pH will remains constant. So for the basic buffer, that means NH4OH and NH4Cl, this solution will contains the excess of ammonium ions and a large amount of ammonium hydroxide and a small amount of hydroxyl ion. On adding acid like HCl, the hydrogen ions added will be removed by ammonium hydroxide. That means H plus NH4OH, it gives H2O plus NH4. Thus the solution suffers no change in pH. When base is added, the hydroxyl ions added are removed by reacting with ammonium ion to form unionized ammonium hydroxide. That means OH minus plus NH4 plus, it gives NH4OH. That means thus the solution retains constant pH. So in acidic like HCl is added, the solution suffers no change in pH, and when base is added, the solution retains a constant pH value. Then we see the calculation of pH of buffer solution for acidic buffer. The pH of an acid buffer can be calculated from the dissociation constant Ka of a weak acid and the concentration of the acid and the salt used. Now the dissociation expression of the weak acid HA is H plus plus A minus, then Ka is equal to HA and A minus upon HA and then H plus is equal to Ka in bracket Ha upon A minus. Weak acid is slightly dissociated with its dissociation in further depressed by addition of the salt Na plus A minus, which provider A minus ions, that means common ion effect. As a result, the equilibrium concentration of the unionized acid is nearly equal to the initial concentration of the acid. The equilibrium concentration A minus is presumed to be equal to the initial concentration of the salt added. That means H plus is equal to Ka upon acid upon base. Taking negative log on the both sides of the equation, we have minus log of H plus is equal to minus log of Ka minus log of acid upon salt. Therefore, the pH is equal to pKa plus log of salt upon acid. This equation is called Henderson-Hasselbalch equation or simply Henderson's equation. Then next, for basic buffer, note that the buffer solution are not ordinarily prepared from the weak bases and their salts because of the volatility and instability of the bases, and also that it depends of their pH on pK, which is after affected by temperature change. Buffer equation for solution of weak bases and the corresponding salt can be derived in the similar manner as that of the acid. Therefore, the OH minus is equal to Kb into in bracket base upon salt. Therefore, POOH is equal to pKb plus log of salt upon base, and also OH minus is equal to Ka upon H plus. Therefore, pH is equal to pKw minus pKb plus log of base upon salt. Therefore, then next we see the buffer capacity. Buffer resists the change of pH of a solution upon the addition of strong acid or a strong base or other agents that tends to alter the hydrogen ion concentration. The magnitude of the resistance of a buffer to pH change is referred to as the buffer capacity. What is the magnitude of the resistance of a buffer to pH change is referred to as the buffer capacity. It is also known as buffer efficiency, buffer index, and buffer value. The buffer capacity is defined as the ratio of the increment of strong acid or base to the small change in pH brought about by this addition. The buffer capacity is expressed as beta is equal to delta B upon delta pH. B is a small increment in gram equivalent per liter of strong base or acid added to the buffer to bring about a pH change of pH. The buffer capacity of a solution has a value of I when the addition of 1 gram of equivalent of strong base or acid to 1 liter of the buffer solution result in a change of 1 pH unit. Then next we see the approximate calculations of buffer capacity. Consider an acetate buffer containing 0.1 mole each of acetic acid and sodium acetate in 1 liter of solution. When sodium hydroxide is added in 0.01 mole of portion, the concentration of sodium acetate salt increased by 0.01 mole per liter and the acetic acid concentration decreases proportionally. The reason is each increment of base converts 0.01 mole of acetic acid into 0.01 mole of sodium acetate. That means CH3COOH plus NaOH, it gives CH3COONA plus H2O. Therefore, the change in concentration of the salt and the acid by the addition of a base can be represented by modified buffer equation. The equation is pH is equal to pKa plus log of salt plus base upon acid minus base. Note that the buffer capacity is not fixed value for a given buffer system, but it depends on the amount of base added, and the buffer capacity changes as the ratio of log of salt upon acid increases with added base. The buffer has greatest capacity when salt upon acid is equal to 1 and pH is equal to pKa. The buffer capacity is also influenced by an increase in total concentration of the buffer constituents, since a greater concentration of salt and acid provides a greater alkaline and acid reserve. So next we see the more exact equation of buffer capacity. Beta is equal to B upon pH. This equation gives average buffer capacity over the increments of base added. Koppel and Spiro and Van Slyke developed a more exact equation is beta is equal to 2.3 C Ka in bracket H3O plus upon Ka plus in bracket H3O bracket square plus bracket square, where C is the total buffer concentration and is equal to sum of the molar concentration of acid and the salt. So maximum buffer capacity is when pH is equal to pKa or H plus is equal to Ka or H3O plus is equal to Ka. Therefore, substituting we get beta is equal to 2.3 C bracket H3O plus square upon H3O plus H3O bracket square. The final equation is beta is equal to 2.3 C upon 4 is equal to 0.576 C. The value is 0.5. Welcome students to our new YouTube channel Pharmatech, the division of